Hey everyone, this is Dr. Walker. In this video, we're going to do the second guided example from video 518 on electric potential energy. We're going to find the change in potential energy of a charge as it moves in an electric field, but the difference from the last example is that this time the field is not going to be uniform. Let's take a look at this problem. We have a positive charge, capital Q. It's at rest over here, and it's a distance of 10 centimeters from another charge, little q, 5 nanocoulombs. This charge here is fixed. And we want to know what is the change in potential energy as big Q is moving to a distance of 15 centimeters away. So the first thing that we need to realize is that charge big Q here is finding itself in the electric field produced by little q. We know that the electric field points radially outward from positive charges. So at this location, there's an electric field, KEQ over r squared, and we can say it's in the r direction. So this charge is experiencing electric force, it's in an electric field. It is not a constant field. We know that the potential energy is going to change as the charge is moving from the 10 centimeter to the 15 centimeter. And ahead of time, you should already ask yourself, is that energy going to increase or decrease? But we will see the answer in just a minute, but I just wanted you to think about whether you already knew the answer to that. So we know that the change in potential energy is equal to negative q and then an integral of E dot ds. We found this in this video. So this is little q here is the charge that's moving and gaining or losing potential energy. So in this case, it's big Q. Big Q is the one that's free to move. So we can write this as negative big Q. And then the electric field is going to be KE, and the field is due to little q over r squared, and it's in the r direction. And then the charge is also going to move in the r direction, so we can just call it dr. And we know that it's going to move from a distance of r1, 10 centimeters, to r2, 15 centimeters. So r1 to r2. So all we have to do is integrate this to find the change in potential energy. We can take the Coulomb's constant and the little q out of the integral, and then we can do the integral. Oh, and before we do that, we know that here this dot product cancels out. They're along the same direction here. So now we're doing our integral of 1 over r squared. Let's see, 1 over r squared dr. And we are integrating from r1 to r2. Just wrote an extra step here. Let's put the KE first. KE, Q, Q. And then the integral is going to give us negative 1 over r. So we're going to integrate that from r1 to r2. So that's going to give us, we can go ahead and cancel out the negatives here. So that's going to give us positive KE, Q, Q, and it's going to give us 1 over r2 minus 1 over r1. So now we can go ahead and plug in the values. We're going to get, I can do it over here, 8.99 times 10 to the 9 times 3 times 10 to the negative 9 was the big Q, times 5 times 10 to the negative 9, right? Or nano is negative 9. And then 1 over the distance has to be in meters, so 0.15 minus 1 over 0.1. And all of this will give us a negative 4.5 times 10 to the negative 7 joules. So as we all hopefully predicted, the energy of this positive charge is decreasing as it is moving away from the other positive charge, and it's moving in the same direction as the electric field.